time in Edinburgh?
Very nice. Yeah, except we were almost blown away on the last day.
Oh, really? Was it?
Yeah, there was a strong wind.
Oh, I see. Yeah.
But no theorems were blown away.
Uh-huh.
The proofs from that.
But Edinburgh isn't windy at all compared to Aberdeen, so I hear. So,
God, if it was worse than Aberdeen, it's hard to imagine.
right. Well, my sister's in Aberdeen now, and she's always making this comparison.
The trains were delayed, so it was quite
Oh, right, but around here, trains can be delayed by leaves on the tracks, right? So
Okay, so.
well, I'm being introduced, right? I see.
Okay, it's my pleasure to introduce Hoil Kim. He will give us a long series of lectures, but I actually have forgotten the title.
Yeah, that's all right. Yeah. Ron being the old gentleman professor is one of the few people who remember the sense of form that we're supposed to have. So, in fact, my intention with these lectures was to try to emulate Peter, and give something very systematic. Of course, it's not going to work. Not everybody can do this. Nevertheless, I thought I'd put in some scattered effort here and there to make it accessible to students.
Can you check this microphone switched on?
Oh, sorry, I switched it off by mistake. When the red light is on, that's on, right? Yeah, so as a result, I think it's going to be very uneven. So parts I'll be just going on and on about elementary things, and then other parts I'll just whisk through difficult material. I'm sure you're used to these kind of things, so maybe it's not so bad. But at least my student James is here, so I'll pretend I'm speaking to him half of the time. We'll start with the first lecture, where I'll just mention some generalities. As many of you have heard, I'm going to study homotopy classes of path from one point to another in various contexts. So these will be homotopy classes of path. From A to B. So also, as a matter of convention, I'm going to write the composition of paths like this. Let me get the order right. I think there are different conventions about this, but I'll write it this way. So if you have a path from A to B and B to C, then you get a path from A to C. Right? So if you have gamma in here and gamma prime in here, the thing in here will be known as gamma prime. Okay? So that's the composition of paths. And in particular, if you take pi 1 of x from A to B, there's an action by pi 1 of x from A to A, which of course is just denoted by pi 1 of x comma A. The loops will go to pi 1 of x A to B. So this will be acting on the right. on the space of paths. Space of loops will be acting on the right. So this, as you know, this turns this guy into a torsor, into a right torsor. Pi 1 of xa. Right. So this is the basic thing, that a basic gadget that I'm going to try to explain in several different contexts. And let's start with the very elementary situation where you just have a topological space of some reasonable sort. So let's say X is a locally path connected space. So the important thing is this relation between paths and covering spaces, which will re-emerge in the different contexts, in different language, that is. And the basic relation is the following. Oh, sorry, I guess I should have given myself more room. Is it okay? Can you see if I write here? Okay. And the theorem is this. Well, actually, first I'll write here. C of V of X, this will be the category of covering spaces. So, in particular, a map from one covering space to another is a commutative diagram of this sort. This is a map. And the relation, the elementary relation from algebraic topology goes as follows. So suppose you have, let me first fix a base point on X, any point. And so X comma B is down here. And suppose you have one pointed covering space. So this is when I write a map like this, of course, this means that Y is a covering space of X, and the map takes the point Y to the point B, which is a pointed covering space. And you have another pointed covering space, so Z comma Z, nothing to this one. Okay. And the theorem, the fact, is that there exists a commutative diagram of this sort if and only if the image of the fundamental group of pi 1 of Z comma Z of Z contains the image of pi 1 of Y comma Z. So regarding covering spaces, when does one covering space lift to another? Right? That's exactly when the image of pi 1 via this map is contained inside the image of this map. So obviously it's a necessary condition, and the theorem is there's a sufficient condition as well. So this is the fact from covering spaces, fundamental groups that I won't prove, because it's in any book. But in particular, if pi 1 of X tilde of some little x tilde is trivial, right? Then if you just look at the definition, if we consider, oh sorry, I said B tilde, B tilde. If you have this kind of situation, then whatever this is, since pi 1 of this guy is trivial, the image in here will certainly be contained inside the image of this thing, so there's always a lifting of this sort. Okay? And that's the situation where we call X tilde the universal covering space. Well, let me make one remark back here already. This map is necessarily unique. So that's another fact from the theory of covering spaces. The fact that maps of covering spaces are determined by their value at one point. So once you know that Y has to go to Z, there's only one such diagram. There's just one such diagram. In particular, this is unique as well. So the related comment goes as follows. People call this the universal covering space, but it's actually not universal in the sense of category theory. The thing that's universal is this thing. The pointed covering space after you lift a point is universal because the universal object, the map that you get to all other objects is supposed to be unique. But if you just looked at category of covering spaces without base points, then it wouldn't be unique. This is what makes it unique. So this is the universal pointed covering space after you choose a point. Now I said something just now about choosing a point, but notice that if you chose another point, just by that theorem again, there will be a unique map from one to the other. So essentially, it's independent of this lifting. Actually, maybe I should write that down what I just said because it's going to come up again in slightly different context. The choice of B tilde in some sense isn't important. Because note, if you had x tilde B tilde mapping to xb, and another, the same x tilde, say, or even another one, x tilde prime B tilde prime, if you had this situation, both of them having trivial pi 1, then there's a unique map from here to here, making the diagram commute, and simply also in the other direction. So both ways it has to be the identity. Right? So in this sense, it is universal, and in particular, if you chose another base point, it would exactly be the same situation. Yeah? So it's independent of the base point, so that's why we forget it most of the time. Yeah? But to make the categorically correct assertion that it's a universal object, you need the base point. Okay. Now, let's introduce the formalism that takes us into a more algebraic setting, that leads us into a more algebraic setting. Suppose you chose some point on x, it could be the base point or some other point. Then we get the functor from the category of covering spaces, the set, this thing called the fiber functor. That's of x. So what does this do? It takes any covering space and sends it to its fiber over x. Okay? So this is clearly a functor on the category of covering spaces. I keep losing my eraser. Move back here. Right. And for the moment, this isn't particularly good notation, but let me denote by P of x, right, will be the set of isomorphisms from f sub b to f sub x for any points b and x. Isomorphism of functors from the fiber functor at b to the fiber functor at x. Okay? And you remember the definition from category theory. What this means, right? Well, so what's an object in here? Let's call it gamma. What it means is that for any covering space in x, there's some gamma sub y corresponding to that, right? Which goes from the fiber of x, of y over x to itself. So for any such covering space, gamma will act on the fiber, but in a way that's compatible with the map between y's.
YB to YX.
Sorry? Oh, sorry, you're right, yeah. I'm doing it the wrong way. I'm making it the fundamental rule. Y sub b, that's right. This way around. You get an isomorphism like this, right? So gamma will consist of a collection, gamma sub y, indexed by coverings of x, of this sort, right? So if you've never seen these things before, you should consider the category itself now just as an indexing set, and this is just a compatible system, like an inverse limit, elements of inverse limits. That's the way one thinks about this. So Px, by definition, is just a set of functorial isomorphisms from Fb to Fx. Yeah? And once again, what does the compatibility mean? It means that if we have another thing here and a map between it, let's call it F, right? Then over here, we can go by gamma sub y from here to here, and then we can go by gamma sub z from here to here. But then F will get us from this fiber to this fiber, right? So this is actually, this it comes from a map of covering space, and this is supposed to commute. So that's what the compatibility means. Okay? So that's what this is by definition. So here's a relatively easy theorem now, with just the formalism that we've just discussed. No other machinery is necessary for this. Here's the theorem, is that there exists a natural isomorphism Px to the fiber of the universal covering space over X. Remember, X tilde was our universal covering space, and there is an isomorphism from these isomorphisms from Fb to Fx to this fiber. I say natural. Now it depends on this tilde. What it really depends on is it depends on B tilde, the choice of the lifting. Yeah? Other than that, so there's this isomorphism between the functorial definition and this relatively concrete object.
The right hand side is just a set.
Everything is just a set at the
so
moment. That's right. Mm-hmm.
Even if you choose X to be B,
Yeah, it's still true. That's right. But you're right. As it stands, but the group structure, so what Markish is pointing out is that when X equals B, this thing is evidently a group. Yeah? But the group structure of this is not evident, although it does have one. So let me give a proof of this theorem. I'm going to put, although this is completely elementary and maybe boring to some people, I'm going to give a proof, and I'm only going to prove this kind of theorem once, because then we'll restate it in, again with different kinds of fundamental groups. Right. Okay, as we said, so what's an element here? We'll call it gamma px. Okay. So this, we said, is a compatible collection. So gamma is a compatible collection of the gamma sub y, one for every covering space of X. In particular, from here, we get gamma sub X tilde. X tilde is the universal covering space, in particular is a covering space. So inside to this compatible collection, there has to be an element corresponding to the universal covering space. So from here, of course, we can get gamma tilde and let it act on our choice of base point lifting B tilde, right? Yeah. And then this will give us an element of X tilde over the fiber over X, by definition. Each of these is supposed to take the fiber of Y over B to the fiber of Y over X, in particular for X tilde. Take this element that we chose as an element of the fiber over X. So this way, we define the map, we'll call it phi, from Px to the fiber of X tilde over X. Right, that's the definition. Okay? So I'll just write it down again. If we have gamma equals gamma sub y, this is going to gamma of X tilde, the value at B tilde. That's the map. Right. So, yeah. So first, let's prove injectivity. Suppose phi of gamma 1, well, phi of gamma equals phi of eta. Well, this implies, of course, that gamma of gamma x tilde of B tilde equals eta x tilde of B tilde by definition. But then we have to show that the entire automorphism is the same, just by that value. But all the automorphisms for all covering spaces is supposed to be the same. That's what the injectivity is asserting, right? So let's take Y to be any other covering space. Covering space. Now I'll take a point Y, little y, inside the fiber of this covering space over B. Okay? And we have to compare the way gamma acts on that point and the way eta acts on that point, right? We have to compare those two actions. But remember, for this point now, so there exists a unique commutative diagram from x tilde b tilde, and this is also a pointed covering space of xb, and there's y here. There exists this unique commutative diagram. And in fact, let me call this map f sub little y. Sorry, let me write it here. F sub little y. By the universal property, there exists a unique map of pointed covering spaces. We'll call f sub y. Okay. I'll continue the proof here. So then here's how it goes. If we take gamma sub y, the automorphism of the fiber of y, right, and apply it to our element little y, right? Okay. Then this is gamma sub y acting on f little y of b tilde, right? Then remember, by the compatibility of this collection, this meant that we can commute these two things except this operation, except we just have to apply it in a slightly careful way. So in other words, what this is first, okay, we call this diagram over here. So here, oops, I guess this is slightly reversed. So just for clarity, just this one, so I'll write this out more carefully. Where should I put this? Sorry, I'll put it over here. So we have x tilde mapping to y in such a way that b tilde maps to little y. Now, I'll put b here, of course, because these lines are the fiber. And this, meanwhile, via p, what was my notation? So for example, for gamma of x tilde, goes over to x tilde of x, right? Okay. And over here, via gamma of y, goes over to y of x. And meanwhile, we'll have f going like this, f sub y. Same map. So this diagram is supposed to commute, right? Because this is a map of covering spaces. Right? Okay, so now returning to this picture. Okay, so let me try to figure out what that says. So first I went using fy from b tilde to y, then I applied gamma. So that's the same as f of y applied to gamma of x tilde of b tilde. Right? And we're assuming that the action of gamma of x tilde is the same of eta of x tilde, right? On this point, that's the assumption at the beginning. So that fy of eta x tilde of b tilde. But then, again, by the compatibility for eta over there, then this will be eta of y of fy of b tilde. Okay. Which, sorry, by definition, again, choice of this is eta of y of y. Okay, so that's the injectivity. Okay, let me just say again what we did. Just by assuming that the value of these two automorphisms on the fiber of x tilde on b tilde is the same, then what we get is that they have to act the same way on the fiber of all of these covering spaces. So that's that assertion. That was the injectivity. For the surjectivity, sorry?
B tilde.
Oh, did I just write something wrong?
B tilde.
B tilde.
Instead of y.
Not y tilde. There is no y tilde.
Oh, why?
Y.
No,
Left
before
of that is a y tilde.
Where is the, oh, this is b tilde. Yeah. This is b tilde. You can already see that it's going to take forever to cover the basic material, but this is about surjectivity. So remember, the map phi is going from this functorial isomorphisms the fiber of x tilde over x, right? That's what we're trying to prove. So we'll take, so now too many tildes, but I'll write little x tilde first. So take any point inside the fiber of the x, right? Okay. Now, then, right. Now, corresponding to that, I have to give some kind of isomorphism of fibers for every covering space, right? So now, take any covering space of this of x and choose a point, little y, again, inside the fiber over B. So as before, there exists this unique Fy, right, that I already discussed, from x to y, x tilde to y, such that Fy of B tilde is this y, right? Okay. So now define gamma of y on this element little y, gamma of big Y on the element little y, so define it to be f sub y of which element x tilde. So then this will be an element inside the fiber of y over x, right? Because y, f is a map of covering spaces. Okay. So now I'll check. I'll leave it to you to check. Right. That for this element, so first of all, so we get a collection gamma sub y. Yeah? What we need to check is this is a compatible collection over covering spaces. And where does that come from? That follows from the fact that this map is unique. Yeah? So if you did this to any two different covering spaces, you get the same action. So that's one thing. And the second thing is, of course, that for this collection, phi of this gamma is exactly x tilde. That's essentially obvious from the definition. That's because the map is the identity map. This Fy is the identity map. And we do it for x2. Okay, so just by general nonsense, what we get is this isomorphism from the functorial identification of one fiber to the other, the fiber of the universal covering space. Right. Now, what did I want to do is that? Yeah, so this is, I guess I pointed this out in courses before, but in some ways, when you construct the universal covering space, so here's a remark, we can construct the universal covering space simply as a union of this pi 1 of x dx. This is actually a possible construction of the universal covering space, and topologize it suitably. And this is essentially what we're explaining just now in some sense. No matter how you construct it, you can interpret it in this way, as a union over x. Right. Okay. Now, we can do this now in different contexts. So let's move to the algebraic situation right away. Maybe I'll keep this theorem up there. All right. One can be very general with these things, but we won't. Let's just take x to be, let's say, x over k to be a smooth variety. And so I don't have to make a bunch of mistakes later or restricting assumptions later. I'll say this is a smooth variety over a field k of characteristic 0. Because otherwise I'll make mistakes later. And once again, now we have the category of covering spaces of x. Except it's slightly different from before. This is the category of finite tau coverings of x. So what does this mean? Again, just a brief reminder. you have a map of schemes, y equals to x, this f now, such that on U, an open affine open subset of x, so this is spec A and this is open, okay, then y over U looks like just spec of B, okay, where B is so it's an A algebra. It's an A algebra, which is so B. Sorry, I guess I should write these properties slightly more carefully. But it's A algebra, which is finitely generated as A module, as an A module. So this is the and locally free. So these two properties, in the terminology of Hartshorne, corresponds to the statement that is finite and flat. And then, but the important condition, well, those are important as well, but the essential condition that makes it a truth is the following. Where you take any prime ideal in A, then we can localize B over P and regard it as an algebra over A over P. And then we consider BP modulo the ideal generated by P as an algebra of AP over P. So this will sometimes denote by K of P and call it the residue field at P. So this is supposed to be a separable K algebra. KP algebra. This will be a separable KP. And notice by the locally free assumption, then this is just BP tensor over AP. That's KP. These all have the same dimension, which is just the rank of B. Just the rank as the dimension. But the condition is that it's separable. So that's the attack. So we'll just be considering the category of maps of this nature. Locally over A, just in this situation. So when we say it's a separable separable algebra over KP, of course, what it means, so it's another way of writing it, is that this is just the direct sum of Fi's, where Fi's are separable field extensions. It's a residue field. Okay. In particular, when we take a geometric point of x, we'll write little x now for a map from some spec M to x, where M is a separately closed field. Okay. When you're in this situation, you call this kind of thing a geometric point. Of course, the image will be some closed, well, not closed, but image will be some point of x. So I don't think I gave a name for it, but will be some usual scheme theoretic point of x. So corresponding to that situation that we just described. Okay. So if you take into account this fact, then the point is that if you take any état cover of y, so this is in the sense that we just defined, sorry, état cover of x, and suppose we take the base change now from y plus spec of m. Then this will be just a direct sum of copies of m, and as many as how many copies? This will be the rank of B, A rank of B copies. Because of this separability, when we go to a separable closure, each of these algebras will just split as a direct sum of as many as the degree copies of M, and this is what happens when you take the base change. And sometimes, so we'll denote this by y sub x. So there's two slightly confusing notations that I'll use. Namely, sometimes this base change itself, which will be just some, sorry, I think I put the spec in the wrong way. This is, sorry, disjoint union. like these guys. Or I have to put the direct sum inside the spec. But anyways, so sometimes I'll just denote this scheme as y sub x, but also a set of points. So we'll also use this notation. Will be used for the set of points. This is harmless confusion, I think. Conflation. So, and then when I think of it in this way, I'll think of it as the fiber of y over x. So as before, then, given any geometric point, this is just described, we just get this functor f sub x that goes from the coverings of x. Now this time, except it goes to finite sets. Fiber functor to finite sets that takes any y. It's fiber of y.
Geometric point of big X.
Oh, sorry. Yeah, thanks a lot. So there's that fiber functor. And so that's and as many of you know, we define the Tal path from between 2 points b to x. Just by definition. Maybe for the moment, sorry, I'll just use the standard notation. I was going to use something else. I'll write pi 1 hat for the hat refers to profile. Sorry, maybe I'll write it out here. From b to x, by definition, will be just the isomorphisms from fb to fx. Right. So a lot of the theory is entirely the same as the topological case. The only thing that's somewhat different is the construction of the universal covering space. Which I'll just briefly remind you. Construction of x tilde. So in other words, the point is that we want to give a description of this similar to what we did before. Of course, in this case, it's just a definition, right? So somehow, when you see definitions like this, it seems very abstract. So we need to figure out how to actually get our handle on it. And so we want to give a description similar to what we did with for topological spaces using a universal covering space. And the construction is just slightly different from usual. Maybe it's easier, depending on how much you like topology. And so the way you do it is like this. So we'll take kx to be the function field of x. Now I'll denote by L some separable closure. Yeah, at the moment I mean geometrically reducible. Yeah, sorry about that. I mean geometrically reducible. Right. Now we're going to use this actually to construct the universal covering space. But before I do that, let me just remind you of the following fact. Suppose f is just some finite extension of kx. At the moment, it's separable because I said I'm going to restrict to characteristic 0 for the time being. So I could have said algebraic closure there. So I'll denote by y sub f, right, of x. This is the so-called normalization of x in f. Meaning the following. So over open set, as before, often denoted by spec of A, right? Then the K is the fraction field of A. So what we can do is we can take B to be the integral closure of A in F. So what we get is this sheaf. We get thereby this sheaf, maybe I'll denote it by curly F, of OX algebra, whose value on any given U is exactly that, the integral closure. And of course, this is functorial in the A's, right? So what we can do is we can take Y to be this relative spec of this sheaf F in the sense that you find in Hartshorne's book. That's what we mean by the normalization. So it's a fact. This is a finitely generated O module. Sorry, A module. And flat and locally free. So this is this fact from commutative algebra, that when you do this kind of thing for an algebra of finite type over a field like this, it's called an excellent ring. So these normalizations are all finitely generated A modules, and since they are inside the field, they're flat and contiguous, so they're locally free. All right. So there's this normalization process. Now, we'll say, so there's this standard terminology from field theory that I'll refer to briefly, because it's not, we don't have to do it in this way, but this is one convention that sometimes relates it to things that we have a good feeling for. So we say that F is unramified if it's unramified in the usual sense. No. And let me put this in quotes. What does that mean? Well, we take inside P, inside A, one of these height 1 primes, and then we look at this BP localized at P over A localized at P, with this extension of algebra. And then the ideal PBP splits up as Q1 to the E1 and QR to the ER, where QI's are height 1 primes in BP. Yeah? So unramified means, in usual sense, all EI are 1. So this is a DVR, this is an integral closure of the DVR, so the usual theory applies, and we have all these decompositions unramified in usual sense. And one reason it's good to put it in this language is that somehow then we feel like we feel more comfortable with various properties of being unramified. That is, so for example, if you have a tower like this, F2, F1, Kx, right? And this big thing is, so F2 over Kx is unramified. If and only if. So F2 over F1 and F1 over Kx is unramified. Well, I guess I forgot to define unramified for arbitrary things and not starting with Kx, but it's obviously the same thing. Yeah. And also, if you have things, I mean, essentially for the same reason, if you have F1 Kx, F2, then you take a compositum inside any larger field. It's unramified. If F1 and F2 are.
Is A in this definition?
Oh, sorry, A was I said it quickly. So spec A is U is an open subset. Right. Right. So now let's go back to that slide over there, that panel over there. Inside here, we'll write L sub U for the compositum of all unramified extensions.
I mean, does this mean you take any equal valuation of AX?
Yeah, that's right. That's the same thing. Any of them will be live inside some kind of open subset. Yeah, as I said, the exposition is going to be uneven.
And it's X is smooth,
X is a smooth
but
variable.
not necessarily projected.
Not necessarily projective at the moment. Okay.
I mean, not necessarily proper.
Not necessarily proper, yeah.
But you only take those valuations we have a center.
Yeah, that's optimal fine open subset of X. Okay.
As taking all the
But in some
local
sense,
rings.
this is not a, I mean, KX doesn't determine X, so, I mean, it's not a clean definition, right? Because I mean,
Okay.
KX does not determine X.
You are defining.
Yeah, sorry. I meant unramified over X, of course. Yeah, that's right, yeah. So that, I mean, it wasn't unramified in the field theoretic sense. So I'm just defining those things that are unramified over X. That's what I should have said at the beginning. Sorry. This thing I erased here, I should have said unramified over X. Yeah. Thanks very much. Yeah. Okay. Oh, so, right. So I guess the point was that I guess I keep jumping back and forth. Before I said that, I should have said the following thing. So if we're in this situation before, so then we had this YF over X. We pointed to the normalization. So the fact is that YF over X is étal if and only if F over KX is unramified over X. Now I'll put that in the previous sense. This is not such an easy fact, of course. This is so-called purity theorem. That if you just check unramified codimension 1, then in fact this is top. Any point that you'd care to look at. So what we do is we look at this compositum, right? And then by combining the previous remarks, so here we have Kx and we have Lu up here. And if we take any finite thing in here, then Yf over X is étal for one thing. So next what we can do is we write Lu as a union of, I'll write F sub I, where each of these F sub I is a finite Galois extension. I hope I'm not forgetting some set theoretical subtlety that's necessary to do this. Anyway, so now having done that, I'll change notation slightly and write X sub I for that Y sub Fi in the previous sense. Sorry about that. I had to use Y for a little while just to set up the notation. And I'll write X sub I for the normalization of X inside Fi. This indexing set here will be some directed set. I is directed. And most of the time, in practice, it will be n, the natural number. Don't have to worry about it too much. So having done this, now we define x tilde to be xi. And so this will be the universal covering. Take this inverse system as being x tilde. So this is the definition. So that's this inverse system. In this situation, we can still discuss fibers. So, of course, x tilde will be equipped with a map to x. In the category, I'm not going to be, at this point I won't be too careful with using the right categorical buzzword. In the category of pro varieties, of course, pro covering spaces is equipped with a map to x. And if you take any geometric point of little x, it makes sense to discuss the fiber over x, which will be simply the fiber of xi over x as a projective system, as an inverse system. For each of these fibers, so you have this system. So, oh, sorry. In this, let me revise what I said just now. Not this. This will be, in fact, the inverse limit of the fibers of xi over x. When I discuss the fiber as a set, it's the inverse limit of those guys. Yeah. And then the theorem is this, that pi 1 because of x from b to x for any 2 points b and x is isomorphic to x tilde over x. Oh, sorry, I forgot one other thing. I again have to choose b tilde inside x tilde over b. Choose one point. Okay? And depending on the choice of that point, there's this isomorphism of path spaces that identifies it with the fiber of this universal covering over x. Okay? Now, that's because I proved I gave proof of the topological case, so I wouldn't have to prove this case. So I'll omit the proof of this assertion.
Stupid question. I mean, is there anything wrong if one literally naively takes the projective limit already on for the x tilde?
No, I don't think there's anything wrong. You get a scheme that way. It's just not in the category of finite covering space.
That's right.
That's right. Yeah.
One could.
No, there's nothing wrong. But the tradition is to avoid it. That's right. That's right. It's just you just take the direct limit of the normalization, and it's the spec of that. Okay, but anyways, the fiber in any case is completely concretely defined object in this manner, and so.
There's a point that is hidden by the children.
Sorry.
And there's a point that's hidden that x tilde, as you constructed it, depends on the choice of the separable
Oh,
closure.
the separable closure, that's right.
And
You have
really
to
you constructed it for that particular geometry, and that's your B.
You could construct it for that thing, that's right. But yeah, so that's a point that I'll return to actually, because it is reasonably important. But of course, I could do another B. It's still true. You're right that I could take that to be B as well. In which case, it would be in some sense this would be the identity. It would be the identity. But that's important when you're doing these identification with Galois groups, of course. But to some extent, I'm avoiding that. We allow this to be any B. Somehow, it's actually important to allow this to be any B rather than that B. And it's still true. But okay, so that's the theorem. So the principle underlying, I won't give a proof, but here's just a quotation. It's the following, proof in quotation. If you are given any pointed état covering, then again there exists a unique map. Pointed covering using standard Galois theory. We get this, and from this, the theorem follows, formally following the exact proof that we gave for the topological case. Now, but this fact, by the way, is convenient for the following reason. So let me now specialize to the situation, and then I won't return to this generality ever again for the rest of the lecture. So let's take K now to be a number field, say. So we could do this more generally as well, but for concreteness, let's start with the situation. And so now X over K is a variety, this one, smooth variety, geometrically reducible. Right. And in fact, I'm going to take B to be a rational point, K rational point of X. And X bar will denote the base change of X to an algebraic closure of K. See, then what we can do is we can take X bar and construct a universal covering of that in the sense that we just discussed. So I'm using the notation consistently. Take X bar and take its universal covering in the sense that we just discussed. But then this of course maps down to X. And if you just look at the formal definition, this is still a universal covering. Yeah? This is also a universal covering. This is universal covering of X bar. This is still, but the whole thing, via, well, I guess this is the Grothendieck restriction of scalars or something, this is still a universal covering, the whole thing. But that shouldn't be confused with one other important fact. And this, when you discuss it casually, often arises with a degree of confusion. So another fact is that X bar tilde over X bar, over X bar, this covering is actually defined over K. Sorry, I'll put the base point in as well. So let me explain again. I chose a rational base point. We'll regard that as a base point of X bar as well, where of course I'm viewing it in this way. Spec K maps to X, and then spec K bar maps to spec K. And so there's this base point. So that's how we identify a rational point with a geometric point, but then the same thing over X bar. So I'm denoting all of them by B. So this is B, this is B, and this is B, sorry. All of them, yeah, I'm denoting with the same thing, as is natural to do. And now we take B tilde to be some lifting, yeah? Which was implicit inside this isomorphism. And the fact is that this covering is actually, this pointed covering is defined over K bar. Yeah? Namely, there exists actually a unique X bar tilde naught mapping to X, such that, so this is where the notation gets really confusing. X bar tilde naught bar mapping to X bar is the previous one. Sorry about that. I couldn't figure out any better way to do this on the, in order to really say what the statement is. Let me say it again. So here's the universal covering of X bar, right? But this map itself is actually defined over K in the sense that there is this pro variety defined over K, and a map to X such that the previous map is just the base change of the previous of this thing. And of course, this map is completely different from this map, and one shouldn't confuse the two things. It's not this universal covering. I'm saying this thing is defined over K. And so one does. So there are several ways to do this. One is a field theoretic way to do it by saying that choice of B tilde gives you a decomposition group, and you take the invariant, that kind of thing. But another way of thinking about it, which is a pleasant exercise, is that one constructs it, is to say that you construct it by descent. Let me just say this in words, and I'll just give examples, and we won't need more than examples. That's why I'm not going to actually give a careful proof of any of these assertions. Yes. But remember, this pointed covering is unique. And this thing is defined over K. B is a rational base point. and x is defined over k. So this is equipped with descent data under Galois conjugation. So when you conjugate this, this will conjugate, but this doesn't change, and this is unique. So that gives you descent data for this whole part. Go back down to k. So that's the kind of one of the abstract construction of this guy. Now, of course, if you're uncomfortable with descent of these Pro varieties, what you actually have to do is take those FIs, intermediate FI, to be, for example, characteristics of fields. Then each of those will separately descend. And you get things like this. But the reason for discussing this was as follows. So there are the obvious examples. So take x to be GM, for example. So this is GM over, say, k, over the fixed base field k. And then we'll take x bar, and to be consistent on this by GM bar over k bar. And we know how to construct the universal covering of this thing. So now x bar tilde, in this case, will be this system. GM bar, I'll denote it with a subscript n to denote the covering map. So what does this mean? So this thing here, this refers to GM bar mapping to GM bar via the n multiplication map, even power map. But this thing, of course, is equal to B tilde, which is the sequence of ones. So, in fact, so this, for one thing, has a rational base point. And there's a B tilde, this is B, and the same B down here. The same B here. But then the sequence of ones also gives you a covering of this thing. And the point is that if you now take pi 1, therefore, of GM bar, from, say, B to any x, from 1 to any x, simple. According to the previous theorem, this is canonically isomorphic. So x bar tilde, the fiber over x. This is the system of nth roots of n, x, of nth roots of x. So tal. Maybe I can forget the accent since Kolyatelan isn't here. Pi 1 is tal of GM with base point at x in particular. This will be just canonically isomorphic to z hat of 1, system of roots of unity. And of course, you can do similar example for elliptic curve. Defined over k. It's exactly the same. The origin will be the base point in that case, and which can also serve as a system of B tilde. And then any path space becomes identified with systems of nth roots of some given rational point, for example, or any other point. And the reason I was emphasizing this is because sometimes, for example, even when you write down this thing, if you insist on thinking about the pi 1 as a Galois group, it becomes very confusing to prove this thing. I don't know if you've looked at those proofs. So it's very, you have to make several identifications, and it looks very confusing to write down this identification between pi 1 and the roots of unity, even when you think of it as a Galois group. But when you think of it as a fiber, it just becomes completely natural. So that fiber identification at the beginning makes the whole discussion streamlined in a number of sense for GM or for elliptic curves. So, by the way, so that's actually also true, even for topology. When you identify pi 1 with covering transformations for a topological space, that's not natural either. And if you examine the proof, what it actually depends on is a choice of a point over the fiber, of a lift of the base point. And both the automorphism group and the usual fundamental group becomes identified with the fiber. And that's the way you actually get the isomorphism between Galois covering transformations and pi 1s even in topology. And so, except now, if you keep that in mind and make it very explicit, then it becomes very natural to describe all these Galois actions on pi 1 in these examples. Okay, so let's stop there and continue with the unipotent theory in lecture.